Today we are walking through the paper titled Meet a Harness End-to-End Optimization of Model Harnesses.
Can we start with the big picture of what this paper is about?
The paper argues that a big part of LM system performance lives outside the weight. The harness is the code that decides what information to store, retrieve, and show to the model, so changing that wrapper can change the final accuracy.
Why was that still a hard problem before this paper?
Because harnesses are still designed mostly by hand, and older text optimizers are a poor fit for this setting. They usually compress the feedback too aggressively, which throws away the source code, execution traces, and failure details that matter when the object you are searching over is an actual program.
So what does Meet a Harness do differently?
Meet a Harness turns harness design into an outer loop search. A proposer model reads earlier attempts, writes a new harness, the system evaluates it on tasks, and then logs the new code, traces, and scores back into the file system so the next proposal can learn from the full history.
What is the key thing to notice in that such loop?
The important detail is that the proposer can inspect the actual artifacts from older runs instead of a tiny summary. The paper reports a median of 80 to file reads per iteration, with source code and execution traces taking roughly equal shares. So this is a history-aware search process rather than a one-step local edit loop. The paper also writes the search target as an explicit objective, so let me put that on the board.
How should I read that objective without getting lost in the notation?
Red H star is the best harness under the task distribution. H is the candidate wrapper code, X is the task input, TAU is the model behavior produced under that harness, and R is the reward. The equation matters because it says they are optimizing the whole harness, not just the prompt fragment and not the model weights.
What kinds of harnesses does the search actually discover?
For online text classification, the paper finds a family of memory-based harnesses rather than one universal template, one representative version. Draft verification makes a first guess from a short retrieved context and then checks that guess against confirming and contradicting examples. Another version, label primed query, spends more context to make the label space and local decision boundary explicit in one larger call.
Why are those two variants both useful instead of just picking one?
Because they represent different operating points on the frontier. Draft verification keeps context short even though it uses the calls, while label primed query spends more context to expose the label space and local contrasts more clearly. The search is finding trade-offs that a human engineer would normally have to discover by hand.
Does the same idea carry over beyond classification?
Yes. For retrieval augmented math reasoning, the discovered harness is a compact for root BM25 program. The outer loop chooses the routing rules, ray ranking terms, deduplication thresholds, and the number of examples to insert, which means even the retrieval policy is being learned by search instead of being fixed by hand.
Alright, what does the strongest classification result look like on the chart?
This figure makes the main classification claim concrete. The Meet a Harness frontier dominates the baselines. The paper reports a 7.7-point gain over ACE while using 4 times fewer context tokens. And the selected harness reaches 48.6% accuracy instead of living on the same trade-off curve as the hand-designed systems.
And how quickly does the search get to a good harness?
This curve shows the search efficiency story. Meet a Harness reaches the final accuracy that OpenEvolve and TDT Discover eventually get after only for evaluations. And then it keeps improving until it finishes more than 10 points above the other optimizers. So the advantage is not only the final frontier point, but also the speed of discovery.
Do those search time gains still hold up when the harnesses are tested on separate data?
That is what this scatter plot is checking. The better discovered strategies tend to stay near the diagonal across datasets like law bench and symptom to disease, which means validation improvements usually survive into test performance. It is not a perfect one-to-one line on every dataset.
What happens once they move to math reasoning?
The math result is strong because one discovered retrieval harness transfers across 5 held-out models. On 200 IMO level problems, the paper reports an average gain of 4.7 points over the no retrieval baseline. So the search is not merely finding one lucky prompt for one model, it is producing a retrieval policy that travels.
And what about the coding benchmark?
On Terminal Bench 2, the paper says the discovered harness beats the hand-engineered Terminus K, IRA baseline on Opus for 0.6 and ranks number 1 among Haiku for 0.5 agents. The chart highlighted in the paper shows a 37.6% pass rate for the discovered Haiku harness, ahead of Kus at 35.5 and Terminus K, IRA at 33.7. So the method is competitive even on a benchmark where teams are actively optimizing their agent stacks.
What makes you believe this is real search behavior rather than much sampling?
Because the paper shows the proposer using history in a causal way. It reads dozens of files per round, notices that prompt and completion flow edits often regress. In the coding case, The winning direction was not a flashy palm tree right, but an environment snapshot added before the agent loop to save early exploratory turns.
So what should I remember as the final takeaway?
My takeaway is that harnesses are a real optimization target in their own right. If you let search inspect full prior experience instead of lossy summaries, it can discover concrete code-level strategies that beat strong manual designs in text classification, transfer and math retrieval, and compete at the frontier of agent IC coding.
So the paper is really saying that better access to past attempts turns harness engineering into a runnable search problem, and the results are strong enough to matter in several domains.
That wraps up this paper walkthrough.